Hello, everyone. My name is John Butler. I'm the Communications Manager for Clean Energy here at Swagelok Corporate, and I'll be your moderator for today's webinar, which is entitled Fluid System Solutions for H2 Applications. Hydrogen must be stored at high pressures to achieve the energy density required for use in fuel cell vehicles and infrastructure. As a result, it presents many challenges as a mobility fuel. These challenges include safety, small molecule containment, changes in storage pressures, and rapid thermal and pressure changes. Understanding and overcoming these challenges is critical for OEMs, station owners, and contractors charged with manufacturing the next generation of hydrogen fuel cell vehicles and refueling stations infrastructure. Today's presentation will discuss the critical considerations for fluid system components, including tube fittings, valves, regulators, and hoses, which are used in hydrogen applications and systems. Before we begin, I'd like to introduce our presenter. Chuck Hayes is a 31-year veteran of Swagelok Company. He has spent the last 25 years developing a wide range of fluid system products. In the past 20 years, he's been exclusively focused on fitting technology for alternative fuel applications. He currently holds 7 patents in the US and numerous patents internationally. He's an active member of the CSA, the committees for both CNG and hydrogen, and has recently been the chair of the HGV Hydrogen Gas Vehicles 4.10 for fittings. He sits on the ISO TC97 technical committee as well. During his time as principal applications engineer for the transportation market, Chuck has supported numerous on-vehicle platform development projects globally. Today, he concentrates most of his time on the development of hydrogen mobility solutions for both infrastructure and on-vehicle applications. So before we get going, I just wanted to let everyone know that we will be taking questions at the end of the presentation. With that, I will turn this over to Chuck.
All right. Thank you, John. So we're going to have a conversation today, and this is a real conversational type of discussion to really go through a lot of different aspects of the challenges of H2 mobility. We've talked about, we will talk about ensuring safe use, small molecule containment, which is one of the most critical items, storage pressures, and some rapid thermal and pressure changes. Those all come together to make containing high pressure hydrogen very difficult. And we're going to talk about some of the characteristics of H2 fuel components, including gas seal performance, tube grip strength for fittings, vibration resistance, material integrity, efficient installation, and some things that can be done to help with that. And we're going to be looking at this in terms of a few different types of products. We'll spend a bunch of time doing some basics to start with, and then build up to tube fittings and tube fitting design, followed by some base discussion on valves, regulators, and hoses. So let's get started. So what's unique about hydrogen? Well, hydrogen is one of the smallest molecules in nature that we have here on Earth. It's not actually the smallest. H2, as it's found, is a slightly bigger molecule than helium because helium comes as H1. But H2 is very, very small. And that makes it really have some unique challenges as we deal with it for trying to get leak-tight fitting connections. First one's, of course, safety. Safety is always number one. That is making sure we don't have escaping gas that can pose potential safety risks. And of course, one of the big things that we're running into in the hydrogen community today is that hydrogen fueling for vehicles is going to be done by your average citizen, not highly trained individuals. So typically when we think of industrial products for high pressure gases and fluids, those are in facilities like refineries and chemical plants that have their own workers that are all trained in safety. Today, your grandmother would be able to walk up to a pump, pick it up, and fuel a vehicle at a very high pressure with hydrogen. So there's additional safety considerations that come into developing consumer handled products. Of course, that when you're talking about leak-tight fitting connections, you've got efficiency to deal with. You don't want to be leaking and losing all of your fuel. Get out to your car in the morning and it doesn't start, or go for a break with your truck and have it not go. And we don't want to be wasting what right now is a fairly expensive commodity. Those prices should be coming down over time, but we don't want to be wasting it as well. So there's a few other considerations. Hydrogen embrittlement is one. Hydrogen embrittlement is a very large concern because a lot of people have heard about it. Not as many people understand exactly what's going on with it. But what it basically means is that hydrogen can permeate into stainless steels and other materials. We'll talk about that a little bit more today and kind of how that process works. But pressure and time can really help cause fissures or cracks within material that the hydrogen then interacts with and can cause it to fail earlier than it would in other applications. So high quality materials are important for that. So those are some of the basics. I like this little graphic at the bottom. And what this kind of shows is the relationship between the size of a hydrogen molecule. So if you were to compare the size of a hydrogen molecule as it compares to a golf ball, would be the same thing as comparing the size of a golf ball to the planet Earth. So how many hydrogen molecules can get into a golf ball is equivalent to how many golf balls could get into the planet Earth, which is a pretty significant number of molecules. It's very, very small, and it makes for some unique challenges. So why do fluid control or fluid system components matter? Operating conditions for H2 systems make it pretty challenging. In order to get enough molecules on board a vehicle or into a processing facility, we're going to run pressures that get pretty steep. Those pressures run anywhere between 250 and 700 bar nominal working pressure. Nominal working pressure means at ambient temperature, that's where those pressures are at. Hydrogen does a few other interesting things. It's a non-ideal gas, so it actually gets hot when you fuel, unlike most other gases that get cold. So during a fueling process on a 700 bar vehicle, the gas will actually get to 875 bar and 85 C over that period. So there's significant dynamic thermal effects taking place within the components. There's also stress and vibration. So anything that's working, if we're talking about the transportation side, stress and vibration come into play. There is compression. Compressors always have vibration involved, and that can always be an issue that needs to be addressed. Of course, we said safety and refueling stations must operate for the consumer. I mentioned that a little bit earlier. Then what's really, really critical is getting something to seal and continue to be able to be remade over time as there's maintenance that takes place is very critical within as we think about long-term longevity for hydrogen systems. That includes both the production side, if we're talking about electrolysis, all the way through fueling and on vehicles. So if maintenance needs to be taken place, you need to be able to reseal that system and do it consistently and and with great results every time. So finally, a quality design and with critical materials will help deliver leak tight performance that'll last for years or decades. So I mentioned safety a couple of times, and I'm not going to go much more into safety. There are lots of things out there. The Center for Hydrogen Safety, which is based in the United States, um, their website is h2tools.org. If you want to learn about safety and hydrogen, they're pretty much the masters in it. They have thousands of pages of interesting reading that will cure insomnia and get you educated onto a lot of the different aspects around hydrogen safety. So I'm not going to go more in depth in that. Okay, so let's talk about leak tight integrity, quality and safety. So hydrogen fluid systems can leak for various reasons. So there can be leaks in the sealing areas where components come together. There can also be leaks in what's called permeation, and that's the movement of hydrogen through materials. However, good design can mitigate the effects of these leaks, but every type of fitting or connection is not made the same. So so we're going to go over a bunch of different types of designs out there, especially in the fitting world, so you can get an idea of what those are and where some of their shortcomings are as we build up to understand what some very good design parameters are. So we're going to start with some very basics and build from there. This is a discussion about permeation. I really like this discussion here. This comes from our friends at Yokogawa, and I like the graphics and I like some of the things that they say with this. But what it shows is, if you look at the top of the screen, that's a pressure side of a system. The big gray balls are representing material. In this case, let's call it a piece of tubing. Inside that tubing, there are grains of steel. Those grains of steel are very, very tight. However, there's very tiny, there can be very tiny boundary areas inside of there that hydrogen can work its way through. When hydrogen is under pressure at a high purity of hydrogen, what will happen is it comes into contact with a metal surface. It'll go through what's called a dissociation. So H2 will become two hydrogen ions. Um, So hydrogen ions are an interesting thing. They're very, very reactive, and my best way of saying it is that hydrogen ion needs an electron in its outer shield, and it's going to go find a friend to hook up with. It was interesting. My daughter was taking an advanced chemistry class and had one of those kits with all the little balls to make molecules, and she asked me, "Why are there more hydrogen molecules, hydrogen balls in this entire kit than anything else?" And I said, "Because hydrogen hangs off of most of the molecules that we have on the planet Earth. It likes to find friends, and it likes to mate up." Now, why is that important? Well, if there's things like, if you see on the right-hand side here, that shows a material that is not fully integral. It has some gaps in it, and it has some breaks. So if there is a point where you've got parts of your material, your base material, or your steel, let's say, that is not that the electron shields are not fully formed, or it's not a solid electron shield within them, the hydrogen can go ahead and attach to those and start to break them apart. This often happens. This is part of the process that also takes place during hydrogen embrittlement. The hydrogen comes in and interacts with the steels, breaks apart some of the bonds within it, and makes the material weaker. It's a very simple way of saying it, but it kind of gets the point across. I do get the question all the time. People say, "Hey, Chuck, does this mean that hydrogen can move through steel?" And that the answer is absolutely yes, it can. But on a standard piece of tubing on a high pressure system with hydrogen, I think the best number I've been told is about 20 to 25 years it'll take it to move all the way through that steel. It will go all the way through, and you could have it on the outside. It's measurable, but very, very small amounts. It's a different story when you deal with elastomers and polymers. It can move through them fairly quickly. So, like a Teflon core on a hose can be fully saturated with hydrogen and allowing hydrogen molecules to move through it in a matter of minutes under high pressure. So, permeation is an important thing. The important thing about permeation is making sure the surfaces that permeate are, for elastomers, for example, are small enough that the rate of the leakage through the number of molecules that get through is small enough that it doesn't affect safety. Okay, so the next thing, let's talk about creating a seal. Um, and when we're creating a seal, and this we'll talk about in terms of a metal to metal seal in this case, one of the things that's very important is eliminating what we call continuous pore structures. So if you look at the bottom, there's three different pictures of two-dimensional looking at surface roughness of materials. So when you have pieces machined, there's a roughness, and when you look at it in high magnification, you can see peaks and valleys. They're there all the time, no matter how clean that surface is. When you have peaks touching peaks, you can end up having small gaps running between that material. When they can interlink around as that seal is made, we call that a continuous pore structure, and it becomes a leak path. Is this a major problem in large molecules? Usually not. They usually plug it up. However, as you get smaller and smaller in molecules, the reduction of those continuous pore structures that build up to an overall leak rate or overall number of molecules that can move through. And remember, whenever we talk about hydrogen, we're really talking about individual molecules and a combination of those individual molecules. And more and more of those moving through these individual pores can cause issues. So being able to squish those together, reduce the number of peaks and valleys, or have those peaks and valleys coming together and making just small voids inside that the molecules can't move through, like the right hand side, really helps to control, in a metal metal seal standpoint, um, a a continuous pore structure. Now, on metal parts, how do we deal with this? Well, we deal with it by having plastic deformation. Plastic deformation means we move material or move the metal in such a way that it doesn't come back. We do this in a lot of different ways. Surfaces sliding against each other will knock off the peaks and fill in the valleys. And we do that to create seals. In these areas, we do this at Swage Locker and our Swage Lock tube fitting, which we'll talk about later, and things like VCR fittings for ultra high purity applications. In valves, we do other things. We need to have plastic or elastic or viscoelastic parts that deform. So when you have rubber and you squish two pieces of rubber, the rubber moves to make a seal, and that's how we knock out the continuous pore structures in those aspects. Okay. Next piece, let's talk about leak paths. So leak paths. This particular graphic and discussion comes out of the Swagelok tube fitting manual. It's kind of fun. I actually clipped this directly out of a Hydrogen Europe document talking about leaks, where they copied it from us, which was kind of neat. So we are, still seen as one of the standards in the world for understanding leaks and leak paths. What you see here is two different styles of fittings. The first one is a chamfer, a cone into a chamfer type of fitting. And the one dimension I really want to talk about is this L dimension. And what you'll see is where that cone comes in contact with the body is a very short distance for the L. Having a long distance for the L allows for a few things to take place. It allows to knock down on the continuous pore structure and allow for better sealing against gas. Now, having been involved in development of fluid system components for years, what we really understand, and one of the things for our design teams is the most difficult thing to do, generally for all of our products, is to uh, maintain and control the gas seal performance. In the Swagelok tube fitting, we have two different places that we control that. We control the L along the body and the front ferrule, and the front ferrule across the tubing. And we'll again talk about that in a few minutes. Okay, so let's put these things together a little bit, and we're going to talk about current fitting technology. Uh, and dealing with hydrogen on the market, in about the mid 70s, there was a lot of work being done by British Oxygen. And I happen to know one of the individuals that started using cone and thread fittings. And this is a cone and thread fitting we're showing here because it seemed to be a pretty good solution. It worked better than a few of the other solutions we'll talk about in a minute. And it's kind of become the de facto standard in the hydrogen world. However, as pressures have gone up, there's some challenges that come into play. And I want to talk about just a few things here. I said the first one is, you see in the middle of the screen, we have a primary seal surface. The way a cone and thread is made is that a piece of tubing is taken, it is machined to put a cone on the end of it that has a specific angle on it. And then there's a thread that's threaded on. It's actually a left-handed thread, so it goes backwards, to be able to put on this collar. The nut comes in behind it, pushes the collar, puts force onto the cone goes against the body, and that's where the seal is supposed to take place. What's supposed to happen is that those two surfaces are supposed to slide together and make a seal. There is an understanding in the industry that cone and threads are interchangeable. However, there are some issues about that, and we'll talk about those in just a second. I like to say that the cone and thread fittings have a weep port on them, and the reason they have a weep port or an inspection port is because they leak, and they can leak over time, and they can leak on makeup. And there's a variety of reasons why that can take place. Another piece about it, you'll notice that the entire system is rigid. There's no way in here for any kind of vibration resistance, number one, or number two, ability to overcome things like thermal expansion rates being different between the components. So a few considerations on cone and thread is that there is no international standard for cone and thread fittings. They kind of grew out of a project that started in the 1919 by the U.S. Department of Agriculture that wanted to make nitrogen. They needed it for two reasons. They needed it for munitions after World War I, and they needed it for fertilizer. Someone designed up this. It was machined back in the day. Over the years, it kind of showed up in a few different places. Swagelok actually made one of the first renditions of it as a formal product in the 1960s, as our Snow Trick product line, and then it continued into a variety of different companies coming around the world, and more or less floated into a fairly standard design in the early 1970s. The problem is today that without having international standards on it, the cones in the bodies can vary from 57 to 63 degrees. What happens when you have dissimilar angles come together? If you have a small angle in your body and a big angle on your tube, what'll happen is they could just seal right on the corner and not actually slide. Vice versa, the other way, if the angle's very steep on the tube and the body's got a very big chamfer on it, when that tube goes in, it can actually bite in and give you what's called a coined surface down below, and actually put an indentation into the fitting. That's fine for one makeup, but unfortunately, if you try to remake it, you've got to make sure that that coin surface always matches back into the coin. That doesn't work very well. So those different similar angles can lead to a single line of contact, and a single line of contact is a term that we use to talk about sealing areas and making sure that we don't do it. The reason is single line of contact means you now just have one area of load that has to prevent all of the any leakage abound around it. That ends up being a very low L that we talked about a minute ago. So a very small L is a single line of contact. The next piece is that the other real problem with the cone and thread can be that coning is often performed in the field. This little picture on the side is a kit we sell because we do sell cone and thread fittings, and they work very, very well in certain industries. Large molecules and in offshore oil and so forth, they can work pretty well. But this kit shows you all of the tools necessary to cone an end. That is not a very consistent approach to be able to get your primary sealing surface. Unlike having it on rigid, controlled, process controlled machines with process controlled tooling, what you end up having is you having a whole bunch of random possible variables coming in, including chipped out tools, including chatter, including putting oil on the parts that are needed to be able to thread and getting chips in the way. So lots of different things can come into play that can cause issues without getting very consistent coning onto the parts. One of the pieces that can cause an issue is if the collar is not put on properly, it can lead to not getting enough load into the actual fitting to get a seal. So consistency on making them up can be a problem. The last piece is that this fitting is very, very susceptible to vibration failure. So in high vibration applications, there is a vibration collar that goes on the back. Unfortunately, it makes the fitting very long. With the vibration collar, it does perform pretty well, and some of the other issues do not come into play. We are hearing things in hydrogen, and we're starting to get our hands around understanding it. And this is coming from some of the largest providers of hydrogen service in the world that they just randomly get leaks. So all of a sudden, a station will set off its alarms because the hydrogen sensors are detecting hydrogen. A technician will go to the station. He'll troubleshoot for 6 to 10 hours and cannot find any leaks. It has the cone and threads it seems to be having a phenomena that they burp, where they relieve a small amount of gas for a short period of time and then reseal themselves. It makes sense with the way the product is put together, and it may make sense also because one of the characteristics of putting together the seal is there's often grease used on the nose of the fitting. Hydrogen likes to push grease out of the way, so a dry or a non-greased wet lubricant is much better for sealing. And so over time you can have a tight system, and then it can not be tight for a while and then tighten itself back up. It makes it a very challenging thing when you're trying to deal with sensing and understanding leaks. So we talked about cone and thread just because that's a primary one out there. Let's talk about some other fittings out in the world, and how they fit within the hydrogen world. The first one we're going to talk about is tapered fittings. These are known as NPT in North America. It's a tapered thread. It is used all over within industry. It's not liked dramatically. However, it is one of the better fitting technologies if you have no other choice within hydrogen. The thing we've learned, and just to give you the ideas, I've read a couple PhD papers on it. The PhD said two good wraps of a high quality Teflon tape like Swagelok Strip Tees is the best way to seal a tapered end. So making sure there's Teflon tape instead of a liquid or um, another type of sealant, it definitely is your best way to go to make NPTs work. What we found is that NPTs, high quality NPTs that are designed to work with each other, that follow high tolerances, is important. Where the threads are manufactured appropriately, will give you the best wedging, what's called a metal to metal wedging, taking place in those threads. The Teflon fills in the continuous pore structures, but the thing is the Teflon tape can't get pushed out like the liquids can. So we do find that 1/4 and 3/8 inch work the best. 1/2 inch can start getting to a point that there's just too much surface area to overcome, and above that, they can be problematic. They can also be problematic on remake. So tapered are out there, they're not the best. We see a lot of requests right now for BSPP type threads. These are RS and RTs in the Swagelok world. It's a parallel thread with a gasketed material up top. We have not done any certification for these yet. We may do some in the future due to the requests. But part of the problem with this is it's got a gasket with a very small piece of rubber in it. Um, Rubber materials in hydrogen are kind of an interesting discussion. When we talk about rubbers, and we certify rubbers, hydrogen will do a couple things. It can cause the rubber to deteriorate very quickly. It can also cause the rubber to swell as the hydrogen moves in and out. And unfortunately, like in a lot of other industries, we can't just say a class of rubber works best. So you can't just say a Buna rubber is the right way to go, or an FKM, or a HNBR. We've done a lot of testing on a lot of different materials, and what we found is that two FKMs might pass and two might fail. It really comes down to the actual manufacturing formula from the suppliers. So you have to get down to the supplier level. Suppliers of rubber are very, very secretive about what their actual formula is. So testing has to be done. There are a few rules of thumb. Excuse me. Um, what we found is that EPDM materials that are peroxide cured, which means it's a higher grade of curing, work much, much better than many of the others. There are new materials coming out of the market every day. There is a lot of research being done. But at lower pressures, FKM, high quality FKM products that have good plasticizers and reduction in some of the other fillers that they use work really well. Lower levels of carbon is fillers. Carbon's cheap and it's used a lot in rubber, but hydrogen likes to follow that carbon up into the rubber. So putting all that together, rubber is important and it needs to be understood. The problem with this fitting is those gaskets are generally available. They're just bought on the general market, and we have no idea what that rubber is coming into them. So it makes it kind of tricky. And when you go to certify a joint, um, it really means there's three people involved. There's somebody who's making the body, somebody who's making the fitting, and somebody who's making the gasket, and all three have to work together every time. That's one of the problematic portions of this type of seal. Lastly, if there's any perpendicularity issue between the hole and the say face, or if the face has any kind of waviness to it, that seal doesn't have a lot of room to make itself up. So there can be problems making that seal. It also has some issues on remakeability. So that's the world with the British parallel pipe or the gasketed fittings, and this is the same on the metal as well. There is another one which is sometimes used primarily in Europe, which is the tapered male into a parallel female. Same kind of issues with taper on taper. It doesn't wedge as well, so it's not as consistent as the NPT style. Then there's this whole family. Talk about the whole family of things that have cones or chamfer on chamfer type of fittings. I show two different styles here, internal to external and vice versa. You'll notice the little red lines inside of these. Those are the sealing areas. Again, one of the problems with getting a good sliding surface to be able to burnish and get a long L on those is making sure those angles match very, very well. They don't always in these designs, and that can make them troublesome. I'll show you a better way to do that when we look at the Swagelock tube fitting. And then on the end here, you see this one that's a ball end. This has become fairly popular in a few different designs on a different type of fitting that because manufacturers like the fact that you can get some misalignment and it kind of works like a ball and socket joint. The problem is that if you go back to, you know, elementary school and geometry and you think about putting a ball inside of a cone, what you'll find is that you end up with a single line of contact again. So balls into cones is a single line of contact, and on hydrogen, that's really something we want to be avoiding. Um, Two more that pop up, and the first one is going to be the O-ring face seal. So an O-ring face seal is a one flat face, a fitting in a groove. They have an O-ring, could be a quad ring, could be a couple of different designs. We understand this very well. The first patented O-ring face seal was actually Swagelock's VCO fitting back in the 60s. It's been copied a lot since it's come off patent in a lot of different ways. This became a very popular fitting design for natural gas vehicles, and then fairly soon after that, it got removed from a lot of the natural gas vehicles because it leaks. The O-ring moving within that particular surface. One of the nice things is that you can bring this fitting up metal to metal, and you can make sure it's assured tight every time. However, you have a lot of permeation through these O-rings. The O-rings actually move under pressure cycles, so they have to remake themselves, so it can leak on one cycle and then seal itself on the next. So O-ring face seals in general are problematic. I've heard from many of the designers, chief designers in the automotive world in Germany, don't even think about O-ring face seal inside of hydrogen systems. So that's a testimonial against them in that end. There's one other one, and this is another good example of a product that works pretty well if you need to make a connection where you have options as to what that connection is. Very often, what we'll see is this is an SAE J1926. It's also an ISO 11926 fitting design. It's a parallel thread with a very interesting little groove, triangular groove in the body, and then the fitting has an O-ring on it. Basically, the way this goes is the shoulder of the fitting comes down into full contact with the body. That creates a certain amount of load that loads up the threads. That's what keeps it from coming out, and the O-ring gets squished, for a better term, into the joint and makes the seal. We found that these will work quite well. We've done a lot of testing on them, and part of the reason we did a lot of testing on them was what we did have people having issues with O-rings squirting out of the part. So between the body and the fitting, you could get an O-ring failure, and the thought was that that was always an O-ring failure. What we found over time in some of the high pressure systems, this is something to be careful about when choosing this fitting design, is that it wasn't actually the O-ring that was failing. What was happening was the load between the body and the fitting was being relieved. And what that meant was is that if you didn't have a high load onto the shoulder, the pressure from the system would allow that fitting to actually start unscrewing itself. By the time you got a gap of, you know, a small amount, the O-ring would then squirt out through that gap. So and that takes about 1,000 cycles, by the way, and we've heard that from the test houses as well. When they fail, they always fail between 1,000 and 2,000 impulse cycles. So how to prevent that is making sure that you're not too close to the limits on what the fitting design is. So there are on 1926, there's two different designs. There's a light duty and a heavy duty. The heavy duty has more thread. That gives us more thread engagement, allows it to have better strength under the body. The other problem is if this goes into an aluminum body, it gets very close to the yield strength of the aluminum. So what can happen is the combination of the load onto the shoulder and the pressure from the body can cause the threads to stretch. So great care needs to be taken on that aspect. The other way that this thing can come loose is that people have a tendency to want to lube up these threads. So if you put a bunch of lubrication on it that's very slippery, you change the friction coefficient on the threads, and that allows it to not maintain the same load onto the shoulder and then work its way off. So care needs to be taken there. If you see problems with O-rings coming out, it's not the O-ring, it's the body's coming apart, and you need to look at your design to make sure your characteristics are proper for that. But as a general rule, if it's done right, they can work fairly well, and they work well over time. And that's a good option for being able to do things like gauges and transducers. I threw this one in just because it's out there. I've only seen a couple people try to use it. There is a fitting that is called a cutting face fitting, where the metal from the fitting cuts into the body. Obviously, that's not remakeable. It's not a solid fitting. I don't recommend it at all. Okay, there's another type of fitting out there in the world. These are described in two different ISO standards. One of them is the ISO 13269 standard. And what these really are is they're manipulated end tubings. So you take this piece of tubing and you use a die to go ahead and make what looks like a ferrule end on it or a fitting end onto the end. It's a pretty clever idea. It's been used in diesel for years, but there's some shortcomings when this comes into the hydrogen world that we've discovered, and we'd like to show you those. You see that there are different designs for the way the cone can look. There's different designs for the way the manipulated end can look. This one in particular, again, has a ball on it. That's not a great idea. This one up in the top right-hand corner looks very, very similar to a fitting we make, which is a port connector. We machine on basically a solid set of ferrules, a solid ferrule on one end, and then it's got a tube stub on the other. We do know, and the first thing we were concerned about when we saw this was under high vibration conditions, especially on the smaller ones, they can break over time. So we were concerned when we first saw this design. And the reason is that this vibration issue and stress that comes in play. Up in the upper right-hand corner, you'll see this is kind of what a diesel fuel rail line looks like. There's 3 or 4 lines. They're about the size of an engine. They take up one side. They transfer the diesel fuel to the injectors. They're usually bolted together and then bolted to the engine. So when vibration takes place, they move with the engine. They don't move separately. In the world of hydrogen, we do things a little bit differently. We have large tank rack assemblies. So like there's a fuel line, happens to be a bent fuel line here down here at the bottom. This would be a fuel line for a light duty vehicle running from the back of the vehicle to the front, where a fuel cell might be in the front boot. Those can have vibration coming in a different way. There's a test to be able to deal with this, and unlike axial loading, uh, flexure testing like X, Y, and Z vibration testing, very, very standard in automotive industry. Fittings don't fail that way. That's not quite what happens. What you need to do to look at it appropriately to understand how vibration is going to affect that is you need to hold one side stable. So hold a fitting in one place, and then put loads downstream from that, down the tubing, to see how that's going to work. Now, if you think about a fitting being held in one place and locked down, that tube can't move X and Y across the screen, left and right across the screen, or else it's going to come out, and that would be bad. So that you consider that to be locked in. So the only degrees of freedom it has left is it can move up and down, and it can move in and out of the screen. We can simulate that by doing a rotation. So this test, which is set up by, it's an ASME test. It's also an SAE test. It's used on all aircraft fittings as well. Is there's a load placed in, and there's a strain measured within the tubing in a few different locations, and that's rotated. Simultaneously, there's pressure on the ID and/or impulse testing happening on the ID. It's a very, very valid test to be able to look at how rotational vibration is affecting a fitting. Where certain fittings are bite style fittings that dive in and leave a stress riser inside the fitting body, those can crack under this test. Also, ones where the nuts come into contact heavily can crack. This can cause issues with things like O-ring face seals, where that face that was supposed to be locked in parallel starts like rocking on itself. So this test really shows what's going to happen when a fitting is in a system where other forces are at play. This is a 10 million cycle test, and it's an important way to be able to look at how fittings are performing. So there's one last thing that we've noticed as we've been looking at some of these manipulated end pieces of tubing that you need to be really aware of. And if you plan on using something like this, I recommend that you do the metallurgy yourself and take a look at them. What this is we did a cross-sectional area of one of these fittings, and just went ahead and wanted to see what was happening. And if you see this little gray picture at the bottom, if you can see those look like grain structures. That's the grain structure of a standard 316 stainless steel. Remember earlier I said grain is very important in a high quality steel, so the hydrogen cannot permeate through it. What we found on one of these manipulated this one happens to be the ID is up above. What we found is that a few different things happened. You'll notice these dark gray areas on the upper right picture. Those dark gray areas are actually burn marks from when the etching is done to see the grains. That happens when there's significant cold working being taken place, or significant cold stresses being put into the material. The other thing is that this is the same piece of tube. So if you look in this center area here, it looks like pieces of paper laying on top of each other. That means that the grains that were nice and pretty in this bottom picture have been totally destroyed. They're crushed together, and that grain has changed the consistency of what this material is. And that can happen when you cold work materials. That means this may not actually be 316 anymore. There's probably a high possibility that there's martensitic phase been added to this, which in the world of hydrogen and embrittlement is in the category of bad. So not a good thing to be taking place, but that's not the biggest problem. And the biggest concern that we're concerned about is the fact that there's already cracks. There's a very large crack that's up inside this part already. In fact, under microscope analysis, there's 9 different cracks on the ID. Now, remember I said earlier that hydrogen likes to get down inside cracks where materials are breaking apart and help them break apart faster. It's called hydrogen-assisted crack propagation. And this can happen within this type of system. So putting cracks into your system before you've induced them or forced it to happen in another way is really not a good thing. Will this fail in your lab, in the lab condition as you're qualifying a system? No, probably not. Hydrogen won't get it that fast. It will happen sooner in the field, and that's really just going to depend on the conditions. So introducing cracks into materials right off the gate is not a good thing. So it's just something to be careful about. If you're looking into manipulated end fittings, you got to watch out for it. So in the last slide, we started talking a little bit more about material integrity. High quality stainless steels are part of the way to make things work. We have worked with, Swagelok has worked with and actually co-written papers with Sandia National Labs. That's the US lab, which is considered one of the gold standard positions on hydrogen and hydrogen material. Many of their papers, when they're using stainless steels and different grades of stainless, those materials are actually provided by us to them, and we work with them actively on a number of projects on a consistent basis to better understand hydrogen and what's happening within those areas. So we are experts and our metallurgists on staff. We have multiple PhD metallurgists on staff that help us develop this. And what we've done is we've developed a patented Swagelok material that we use for all of our components, almost all of our components. There's a few exceptions, but when we're talking about stainless, we have a 316, 316L stainless steel. It's co-certified. And what we do is we control very important elements. One of the first ones is nickel. Nickel content is controlled at 12%. That helps maintain the crystal structure within the steel, and then we maintain our chrome levels at 17%, which helps on corrosion resistance. We also control the moly and the sulfur. Those all help with both corrosion, crystalline structure, and maintenance of those materials. There are some people that talk about other types of stainless. There's a lot of talk about 13% nickel or nickel equivalencies, which is a combination of all the different alloys involved. We feel that that's not necessary. 13% nickel is the higher nickel is the better, but there's a level of gain that you will lose being able to add the other alloying elements like chrome to a 13% nickel material. It's much more expensive, and right now nickel is very, very hard to get. Much of the nickel in the world was coming out of the Ukraine, so the nickel's been spiking very high on the market at this point in time. What that means is if you just look at a standard 316, people making standard 316 are going to make it as close to 10% as possible. 10.1% is what you usually see if you buy just a non-certified material or a material on the market which was not made to a specific standard. All right, so we've talked about a lot of things there. Let's talk about Swagelok tube fitting and what is able to be done to solve a lot of these different issues. It's an all-metal construction. There's no elastomers within the Swagelok tube fitting. It got great performance in a lot of different aspects, and really there's no loose pieces that you have to deal with once the fitting is made up. So the Swagelok tube fitting, everything on one screen. I'll show you what this is. We've got three big things we talk about. We talk about tube grip, gas seal performance, and vibration resistance. Tube grip and vibration resistance are both come from the design of our rear ferrule. Our rear ferrule has evolved over the last 75 years to the current design, which is actually, it's designed to have a hinge and collet as it goes ahead through its design. Swagelok tube fitting is axially made, so all forces go in an axial direction, nothing spins. What happens is the rear ferrule drives behind the front ferrule, and as it does that, it actually turns and it dives into the tubing. So it does get a grip into the tubing, and that has taken place by having a hard surface on that rear ferrule. We do that through a patented process called SAT12, and I'll talk about that in a second. The front ferrule actually has a differential angle between the body and the angle on the ferrule. As the rear ferrule drives it, it lifts up slightly, allowing it to burnish along that edge and get even a tighter seal there. A long L and reduction of continuous pore structure. Same thing happens along the tubing. It drives along the tubing and is able to go ahead and burnish that surface. So we get a very solid gas seal performance, metal to metal, right along both of those surfaces that is able to hold back the hydrogen at acceptable leak rates throughout. The cool thing is that when you put this together, you pull it up a turn and a quarter, and it's done. It works every time. That will get you up to anywhere between 400 and 600 or 700 bar, depending on the tubing that's being used. So when you have to go up higher, we're getting to 700 bar systems and systems that need to be holding up to 1,000 bar on infrastructure. We have a different design, a slightly different design. This is known as the FK fitting. This fitting was designed, I was actually part of this design team back in 2004. Back then, remember, I think George Bush in the US wanted a hydrogen economy. There was a lot of push for starting to head towards hydrogen vehicles. The problem was fuel cells weren't quite ready yet. This was designed for an on-vehicle hydrogen application. So it is a hydrogen designed fitting. You'll notice a few differences. It comes on this plastic arbor. You can see the front ferrule here, the back ferrule's tucked into the nut. The nut is a male design in the nut, and we do that so we can add a little bit more strength into the body. It's got superior vibration resistance and tube grip. And what you'll see on this, a little bit different than the other one, this back ferrule looks different. It doesn't have, you can't see the hinge. It actually hinges, it still does hinge, and it collets inside when it's made up, but it's much more robust to be able to handle the pressures that we're talking about. The front ferrule still does the same. It drives along the surface. It drives up, drives along the surface, burnishes, gets a very long L, but all along the tubing, it does something a little bit different. This actually drives under the surface of the tubing to get below any imperfections that might be in the tubing and create its own sealing surface. So much more robust when you have issues with tubing. It also assists on tube grip. So tube grip, of course, is part of the whole pressure, holding back the pressure. Now, this particular fitting is designed so that you can take it out of the box, go ahead and place it into the part, and pull it up one turn, and it's going to hold 4 times burst pressure of 20,000 psi with the right tubing. Burst pressure and pressure ratings for fittings are always based on the tubing. Not the fitting itself has a rating based on the tubing. So as walls get thinner, things change. The pressure ratings can change as well. Um, the other thing about this is you'll notice there's a nose on here. This nose comes in contact with the body, and that contact allows it to slide and give us a torque spike. So it is a makeup by torque as well. I mentioned SAT12 earlier. So SAT12 is a process we use, which is called low temperature case carburization. What this does is we take stainless steel. This is a ferrule nose, if you see it in cross section. What we do is we take and we strip off the oxide layer to allow us to be able to force carbon into the surface. The carbon gets super hard, but we do it at a low enough temperature that we don't create carbides. That gets us tool-like hardness on that, and then the ability to have high levels of corrosion resistance. Most importantly, though, that as this moves through plastic deformation, it does not crack. So remember, cracks cause hydrogen to be able to enter into the products and cause issues. There are other ways to harden stainless that are chemical, but they crack as soon as they start to move. So that's not a great way to make that work. So it really adds to wear resistance and gives us a very hard surface. So up near the surface, where we've added all the carbon, we're up into a Vickers scale, Vickers 25 scale of 900 to 1200 Vickers, which is really what tool steel is. And that can get down into, we've added hardness down into the area of 20 to 30, 40 micrometers into the part. So overview, let's talk about fittings in general. So good fitting design, diligence in all aspects of the design is needed. So, key takeaways is that we need to design for tube grip and gas seal performance. The long L for the sealing surface and contact are critical. Reduction in continuous pore structures. Machining quality and high quality machined components is critical, and surface finisher. And then that burnishing action really makes the difference of finishing that metal to metal seal area without having to use elastomers. Material selection with 12% nickel and 16% chrome makes for a very effective prevention against hydrogen embrittlement. The SAT12 process allows for those parts to slide together and go ahead and get our hinging and collating action to work properly, and then give us a good tube grip. And finally, being able to remake fittings by either turns or torque is critical. All the switch tube fittings are able to be remade 25 times minimum, and have been certified to that through hydrogen standards. All right, so we're going to move real quickly into just a few different design factors as we look at other things. So let's look at valves. Ball valves and general ball valves within the hydrogen industry. Ball valves have to be careful about design and considerations for them. There are lots of ball valves that work really, really well below about the 500 bar or 450 to 500 bar threshold. Once we get above that, ball valves get a little bit trickier just due to large surface areas that are coming into play, large continuous pore structures, and then deformation of what those seals look like. Seals in valves have to be some sort of elastomer or viscoelastic. So you're looking at PTFE or rubber types of seals, and you need both seals on the ball and seals on the stem. So making sure that the quality of that design is good is really important. Then, of course, the ball has to have very good surface finishes. We do have one that works very well, which is an FKB ball valve. This has live loaded stem designs, live trunnions for the ball. It's a trunnion ball, so it's not perfectly round. It's supported top and bottom, and this works very well in dispenser applications. It's used extensively in Asia right now on 350 bar dispensers. We do have it in two-way valves that are bidirectional. We have some three-way valves that are primarily manual that would be used for blowdown and so forth. And we get flow characteristics between 0.4 and 11 CV. So it will work well in different applications. We're working some improvements as we get into high-speed actuation for higher pressures, and those improvements should be coming out in the near future. So if you're considering using those, we want to talk about that a little bit on the high-speed actuation. Just due to the nature of the way the stems are designed and the way the hydrogen works. So needle valves, there's lots of different types of needle valves. This is showing a small instrument needle valve, and things that have to be considered is the stem packings. So you're constantly moving up and down along the stem. You do multiple turns, open, close. You have a stem going into a chamfer at the bottom. That goes right back to all the conversations we had with stems and bodies. At some point, something here is going to deform. Usually what you want to happen is you want the stem to deform so you can change out a stem and continue to keep your body in play. So there's lots of different styles of needle valves, again, going from low pressure to high pressure. Seals are important as to what those seals are in the seal materials, especially when you're dealing with elastomers and polymers within them. So some of the considerations that come into play, actuation, of course, comes in too, to make sure there's enough actuation force to keep the pressure from the system from lifting up the stem when it's pressurized and closed. We have needle valves that come from our IPT family. We call these the NV and NVT series. These have PCTFE or PTFE packings. The temperature ranges work well. We make a lot of different connection sizes. The whole family of needle valves, ours, everyone else's on the market, all came from the same applications in oil and gas. They work relatively well within the hydrogen world, depending on how the application is done. We're right now working on and doing some improvements with these to even make them better, make it easier to change out stems, work on improving some cycle lives over time for things like dispensers and otherwise potentials for a little bit difference in the way the seats work, because they do take very high forces. So if you're looking at 1,000 bar, it takes in gas, it's a very high amount of force on those seats to be able to keep them sealed. Again, metal to metal seat. The one nice thing about ours is that you can get FK ends on them. That's the best part about it. So we're the only ones that make a needle valve to get FK, and FK is by far, I feel, superior fitting inside of a system design. This is what they look like from the inside. You got needles, you got regulator tips, so those can be used to throttle flow, and then you've got your standard just needle, and a variety of packing in the stems, and then of course you can add actuators to the top. There are check valves, and check valves are important inside systems. The one thing to be important about check valves is what the elastomers are for sealing. Be aware that springs will wear out over time if you're doing high actuations on them. We did have a customer came back to us and said, I have a check valve that failed in 5 months. We asked how many cycles was on it, and they said about 15 million. And I said, congratulations, you just found your mean time to maintenance. Springs in check valves have a tendency to be very light because you want it to open with very little force and then be able to close quickly under other force loads. So understand that with check valves. We're actually working on some new designs specifically for hydrogen on check valves, so keep your eyes out for that coming out in the future. This particular check valve is a CH series check valve, and it's certified for on vehicle for 350 bar applications. It's got a poppet on the end with an elastomer seal that goes ahead and makes that seal, and the body seals are both elastomer with Teflon backup rings to be able to secure us to the environment. Finally, we're working on, I said again, we've got some other check valves that are working at higher pressures. Again, types of things that were originally designed for oil and gas that are being approved right now for hydrogen and small molecule gas that'll be moving forward. Regulators, regulators are becoming an issue right now in the industry. They're just, as we work through on vehicle, the single set point regulators have been needing some improvements. We're working on improved ones right now. We have multiple regulators in test labs right now with hydrogen that'll be released a little bit later this year, early next year, that are really optimized for it. The big thing about regulators is, of course, you've got a lot of different seals within them, and those can be elastomer as well. So picking the proper elastomers and picking the right sensing area to be able to maintain that flow rate appropriately, and the pressure within the system as needed. We've had very good success in all of our testing, and there'll be better designs coming along with this to help out in the entire market. But we have applications right now that can be used at a variety of different pressures. Sales and service centers can help with that. Our KPR series is one of them that we're working on right now as an updated regulator for our hydrogen industry with metal-to-metal diaphragm seals internally. We are also working on a ramp regulator for fueling systems. That's out of test right now at the external test lab for hydrogen, which creates the ramp, and we'll have more information of that coming later this year. So hoses, just basically some of your hoses, your really flexible stuff, has Teflon cores. Again, just be aware the Teflon will permeate. When dealing with low pressure, your best thing is always an all metal hose with a convoluted metal ID and over wraps and welded ends. We use these very successfully throughout the industry. Highly recommend them up to about your 100 bar zone, depending on what sizes we're looking at. So a variety of series, including our FJ all metal hoses, can work within these systems, and oftentimes used for that final connection on vehicles between the regulator and the fuel cell for isolation of vibration. Okay, so I'm wrapping up. We're coming up on time here. So understanding long-term viability within the hydrogen market requires good design and safety and reliability for vehicles and infrastructure products. Swagedock offers a large variety of products today. We are actively working on portfolios and actively have engineering teams to make better and better products to work within, especially the 700 bar market, the market for 350 bar, and especially on the lower end for production. We have tons of products that have been working in that industry for 30 to 40 years already. So the higher end stuff is where we're helping to create better and better products, and we'll be keeping an eye out at that in the future. And with that, I'm gonna pass it back over to John. John, if you'd like to hit us up. I know we've only got a couple of minutes left for some questions, but people want to stay an extra minute or two, they can get some of that.
All right, thanks, Chuck. Great presentation. I don't see any questions currently in the chat. So if you have any questions, we've got a couple minutes yet. Please jot them in there. One question that we had that was submitted earlier is what challenges are presented by thermal changes in the H2 fueling system delivery process?
Oh, it's a great question because during fueling, well, I'll use the example of a 700 bar system. In order to get the maximum number of molecules on vehicle for fueling and do it within a reasonable time, a vehicle would come up, let's say it pulls up, ultimately it's going to have 700 bar in the tanks when it's done. That's the plan. So let's say it comes in with 20 bar, so we're pretty empty, pulls up to a station. A station's going to plug in, and the first thing it's going to do is do a leak check, which is actually something really cool in hydrogen, that we do a leak check every single time a vehicle is checked, is hooked up to a station, to make sure that there's no leaks in both the dispenser and in the vehicle. In fact, there's up to 3 leak checks done on every fueling cycle. But once that's checked and it's not leaking, it'll start to flow gas. Now the protocol is that gas starts at minus 40 degrees C. So it's very cold. And what it's going to do over the next 3 minutes, 3 to 5 minutes, is go all the way up to 85 C. That's a large thermal shock to hit your system. What that can lead to is if you've got dissimilar materials, they can shrink and grow at different rates. That can open up gaps that can temporarily leak. So having good system design throughout that entire aspect is really, really critical. Metal to metal with the availability of things like our rear ferrules actually give a slight bit of flex to allow for some of those changes to happen dynamically within the fitting design. It'll go up to 875 bar actually at the final fill. At 85C, when that cools back down to room temperature, it will be 700 bar in the tanks. So it's a large spike of both pressure and temperature simultaneously. Those are two nasty things to happen from an engineering standpoint, and that happens in 3 to 5 minutes. Then it'll all cool back down to ambient and do it again the next car that pulls in. So they're constantly being subjected to two pretty difficult engineering challenges: pressure and temperature.
Okay, thank you, Chuck. It doesn't seem as though we've got any additional questions and we're up at time. So I'll just leave you with the following thoughts. You can request more information from swagelok.com by submitting a form. A representative from your authorized Swagelok Sales and Service Center will reach out to you within 3 business days. An on-demand version of this webinar will be available on swagelok.com in the coming days. If you have any trouble locating the link, please feel free to reach out to me directly. And with that, I will thank you all for attending today's webcast. We hope that you found it helpful and informative, and we will wish you a great rest of your day. Thanks for joining us.
Thanks, everyone.